So today we will cover some examples related to the internal and the external hinge, and we'll do that interactively. So I'm just changing my camera to the document camera. You see this. So just now a plane had gone above my head, and you must have heard the noise. So whenever plane comes, so what I'll do, I'll give you a small pause. So just bear with me. So I'll be here itself. And so today we have, let's take one example. I hope you have tried it also at home. So this is a frame, a very simple frame with all dimensions L. And it's under UDL, and here I create a hinge at the beam column joint. Now because here just two members are meeting, it's not that we have hinge in either beam or column. Both will have hinge definitely, because here only two members are meeting. When there are three members meeting, then we may have hinge in one and not in two others, but here we'll have hinge in both. So how do we solve this problem? So there are two ways of doing it. One way is that we just use the normal member stiffness matrix. So we'll use both the methods. Method 1, we use the normal stiffness matrix, and method 2 is that we use the modified stiffness matrix. So I am using here star, just like in moment distribution method and slope deflection method also. When we use the modified approach, we use a star. So here also we'll use that. So we first use method number 1. So in method number 1, what we have to do is that we have to identify the degrees of freedom. So how do we identify the degrees of freedom? I am just marking here. So we begin with the unrestrained joint. So we have the degree of freedom 1. So I'll be using double arrows to mark the degrees of freedom. And then we have the vertical translation. So the horizontal translation and the vertical translation, they are common to both these members. So we also do marking of the member. So this is member number 1, this is member number 2, and this is member number 3. And now when it comes to the rotation at this joint, we have two possible rotations. Now both the members will have independent rotation, so that's why there's a duplication, 3 and 4. So we have an additional degree of freedom here. So in method 1, which we are doing, we have an additional degree of freedom. So this is method 1. So we create duplication of the degree of freedom. And then coming to the next joint, we have here the degrees of freedom. Please mute yourself. Dr. Dhawan, please mute yourself.
Okay.
So we have here the degree of freedom number 5, number 6, and number 7. So we have one additional degree of freedom here. So that's the thing here. So after this, what do we have to do? We have to, because we have here member load, so we have to obtain the equivalent joint load. So we break down the structure into two parts. So part number 1, or we say part A. So A is that we restrain all the degrees of freedom. So we have applied here restraint, and at the two ends of the member, especially the member which has the load. And what we do, we find out the fixed ended forces. So this is our structure number A. So we find out the fixed ended forces. So these fixed ended forces, they are WL by 2, WL by 2, and then we have the moments, fixed ended moments, WL square by 12. And equal and opposite of these we apply on the original structure, because now we have done here restraints, so we have modified the structure to restore back. We apply equal and opposite of these on the structure. So remember that we have restrained here the rotation at the hinge also. So now we apply equal and opposite of these on the actual structure. So I am just using blue color. So we have applied here WL by 2, WL by 2, and then the moments will be in opposite direction, WL square by 12 each. So what you find here now, if you try to superimpose these two structures, then we get the original structure, because then these external or the extra moments and these forces, they are cancelled out, and what we get the original structure. So that's why we have done. So this is our structure number B. So now what we'll do, we'll analyze structure number B by the matrix approach or the direct stiffness approach. Is a new document camera. I am pointing the mouse, so I am now shifting. So what you find here, that this structure we'll analyze by the direct stiffness approach, and whatever results we get, we have to superimpose the results with structure A. And structure A, what is the result? Result is that only this particular member is affected. It has these member end moments and the shears. So these have to be added in the final result we obtain by analyzing B. So that's the only difference we have to keep in mind. So now what's the next? Next is that we can form the KTS, and we know that we have already identified the degrees of freedom. So my question is, you can unmute yourself and tell me what will be the size of KTS.
13 cross 13.
13 cross 13.
Yes.
13 cross 13.
13 cross 13.
Yes. Because we have shown here the degrees of freedom corresponding to the unrestrained joints. We also need to mark here the reactions. So 7 we have done. So I am using black color. 8, 9, 10, 11, 12, 13. So in between, yeah, I am also getting the here notification that in between sometimes the network quality is also bad. But whatever the case, if I encounter that network quality has suddenly gone bad, that time I'll just give a pause so that you don't miss anything. So that's the issue with the synchronous method. Synchronous method, anytime planes can fly by, or the network quality could be bad. But in the asynchronous method, I record in the night time, 10 o'clock, there are hardly any planes, everything is very peaceful. So no noise, no barking dogs, and nothing like that. So yes, so this size will be 13 by 13, and we can do partitioning also. So how do we do partitioning? So what will be size of KPP? You can just unmute and inform me the size of KPP and KXX.
7.
Yes, it will be 7 by 7 and 6 by 6.
KXX.
Yes, so 6 by 6 KXX and KPP 7 by 7. And then after this, what is the next step? Next step is that we have to form the load vector or the force vector corresponding to structure B. So that will form. So force vector will have now 13 terms. So let's make a matrix, and then we'll keep on filling the values for this. And I just draw a shorter one so that all 13 can be included here. So this is our force vector consisting of the two components. One component is P and other is X. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 and 13. So let me write. Also let me use a pointed pen. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So can you now guide me what values do we fill up in at cell number 1? So we have to see what load is there along the degree of freedom 1. So there is no load. So we have to just concentrate on this structure now. Structure number B only. For matrix method, the direct stiffness approach, we just concentrate on structure number B. So here we will fill up 0. And then in the second unit, what do we fill? You can keep on, if you can unmute and let me know. So here we will fill minus WL by 2.
Minus.
Right. At 3, what we will fill?
Minus WL square by 2.
Now you have to be very careful. At 3,
0.
0, yes.
0, sir.
Because
Zero.
the member load is not contributing anything to the rotation associated with the column. It is only contributing everything to the rotation associated with the beam, because the member load is on beam. Alright. So here on beam, what value will fill? Minus WL square by 12. Alright. Now member number 5, sorry, cell number 5, 0. Cell number 6, minus WL by 2. And cell number 7, plus WL square by 12. So hope you now see a difference, that this is now plus. It's in the same direction as the positive direction of 7. So that's why it was 7. And all others, now we have x values, x8, x9, x10, x11, x12 and x13. So this is our force vector. I am just flipping here so that you will see the other terms also. Okay. And once we have done it, now we have to form KTS. Right now we just create KTS and initialize all values to 0. Now we have to form KTS. So how do? We do one by one recursion loop. Member number 1 will send all its elements, member number 2 and then member number 3. So before that we have to form association matrices. So let's form association matrices of these members. So I am just writing here association matrix. I am just drawing a single matrix I am making, and for 3 members, 1, 2, 3, 4, 5, 6. So we have 3 members. So all 3 members we can form the association matrix, and I am writing here this 1, 2, 3, 4, 5, 6, the numbers, that these are the numbers related to the member degrees of freedom. So what values will be filled? Values will be filled here, the degrees of freedom corresponding to the structure. And this is for, we just write, this is for member number 1, member number 2, member number 3. Alright. So now you guide me what values will be filled.
There should be
Yes?
Sir, there should be the 7th degree of freedom to the
There should be
the 7th degree of freedom.
these 1, 2, 3, 4, 5, 6. They are basically the member degrees of freedom of member 1. Member 1 has only 6 member degrees of freedom. We are not talking about structure degrees of freedom here. Member 2 has also 6 degrees
Okay,
of freedom, and member 3 also has 6 degrees of freedom. Now here inside these cells we may fill up the numbers. So one by one they will be different. Now for example, member number 1, what are the structure degrees of freedom? They are
6,
1, 2, 3.
8, 9, 10. Let's say this is our end. This is our first joint and this is our second joint. So that means we are assuming that the x-axis is vertically upward. So we are assuming that x-axis goes like this And where will be y-axis going? To the left or to the right? Local y-axis.
Right side.
Local y-axis will go like this.
Right
That's
side.
why x cross y is z towards the user, towards us. Alright. So from bottom to top. So here what we'll fill here 8, 9, 10. And what will be coming in 4, 5, 6 cells? 1, 2 and 3. Alright. And for member number 2, can you anyone dictate me the values for member number 2? Yes, 1, 2, 4, not 3. 1, 2, 4 and
1, 2, 5, 6, 7. 5,
5,
6,
6,
7.
7. Now who had asked the question of 7 in the beginning? Now your doubt is clear. So 7 comes here. The 7 number will come here because inside these cells we are filling the structure degrees of freedom. But the cells of these, they are only 1 to 6 only. Okay, now member number 3. Member number 3, we assume again that our local x-axis is like this and local y-axis is like this, just like for member number 1. So here what will come? 11, 12, 13 and 5, 6, 7. Alright, so this is the association matrix. Now we can very easily transfer any element. Let's say I give you an example that for member number 3, where will the element k of member 3 6, 6 go? Where will this element go? 6, 6 for member number 3 in the KTS. Where will it go? Yes, it will go to 7, 7. How? Simply we have to see
7,
6. There is a plane. I am just pausing. Yes, gone. So we just have to see in 6, 6 what is the value? 7.
Please repeat again,
So
sir.
6, 6 will go to 7, 7. So that way we form the total structural stiffness matrix one by one. So after we form the total structural stiffness matrix, we have to solve the equations. And what are the equations? Equations are, there are two sets of equations, P equal to KPP, UP plus KPX into X. Alright, sorry, KPX into UX. And UX is 0 here. So you can get UP, and then the next is reactions. Reactions are just K XP into UP. The other part is 0 plus KXX UX, this is 0. So we get reactions also. After we have got UP, after we have got the reactions, the next step is we have to find all the member forces. So all the member forces are to be found. And how do we find the member forces? Because we have all the now the displacements. So all the displacements we convert first in the local coordinate system. By the transformation process. And once we have the displacements in the local coordinate system, we find the member end forces. Alright, so these are the member end forces in the local coordinates, but this result is for structure number B only. So we have to superimpose what? We have to superimpose case A also. That is called as correction. We need to do member end force correction for structure number A, the fixed ended case. But remember here that the case A is like this. We are fixing both the ends. So we are fixing both the ends. So there will be only force correction, end force correction, no end displacement correction. Alright. But suppose in this case you could have chosen your fixed ended structure in a different form also. In the same method, one would say that why I choose like this. Let me choose my fixed ended condition like this. That I am just redrawing some parts. That this was our structure with the hinge, and we had a loading, and we had the numbering. I'll just renumber the degrees of freedom also. Let's say someone says that I want to break it down in this fashion, that this is my A and B. So A I do like this, that I fix this end, but I keep this as hinge. I can do like this also, fixity. So I say that this is my structure A, and structure B would be equivalent opposite of this on the real structure, plus this is my structure B. So all we have to do is, now the fixed ended forces will be different. What will be this? This will be 3 by 8 WL. This will be 5 by 8 WL. And this will be WL square by 8. So they are different. So on the this structure, equal and opposite will act. So here we have 3 by 8 WL, here 5 by 8 WL, and here we have WL square by 8. So in this particular case, the force vector will be different. Force vector will be different. That if we are now drawing part, we'll just draw part of the force vector. This is still method number 1, but with different structure A. I mean method 1. I'm just writing here method 1, but we have different choice of structure A. Alright. So here if we now draw the force vector P and X, at least P part we can form. X part will remain same. So P part, what will come here now? 1, 2, 3, 4, 5, 6, 7, and remaining we leave. So what will come in the first cell of the force vector? Can anyone guide me? 0. Second cell, it will be minus 3 by WL. Now it has changed. Number 3 is again 0.
3 by 8
minus 3 WL.
And number 4 will also be 0 now. Here it is now 0. So it's different from the previous case. Number 5, 0. Number 6 will be this. So minus 5 by WL. And number 7 will be WL square by 8 plus WL square by 8. So values are different, and we have to solve in the same manner. So here what we have done is that we have assumed here hinge in both the structures, that in the locking condition also it's hinge, and in the when we apply equivalent opposite, that time also is in hinge, that is structure B also, both cases it's hinge. So when we superimpose, so hinge will remain hinge, so nothing will be added. So the final member and moment here will be 0 automatically. But then when we do correction, so in the end when we get the displacements, member and displacements and member and forces, so we'll first get D. So this D will include all the displacements, including this rotation also we'll be getting. But then we have to apply correction here also, because here this particular case the structure is deforming like this, it's undergoing deformation like this. So we have to apply this correction for this fixed ended case rotation we have to apply. This has to be done in the end, that we need to do displacement correction also. That force correction we do, that we add the force corresponding to the fixed ended forces. This is force correction, and then we do the displacement correction also. So we have to do both force and displacement corrections. So this is understood. If you have any doubt on this, then you let me know, because now we will start the second part, that is method B. If you have any doubt, just you can unmute yourself and ask on this.
Excuse me, sir.
Yes.
Excuse me, sir. Sir, could you please explain the load vector once again for this?
For the modified case, method 1 with a different choice of A, right? So what we have done, we have
Yes, sir.
applied fixity, but we have not locked the hinge deliberately. So hinge is like this, and what we get, because we have not locked it, so the reactions are different: 3 by 8 WL, 5 by 8 WL, and WL square by 8, because it's like a prop cantilever case. I'm just pausing for a while because I'm getting signal of bad network quality. You may not hear. Okay, gone. Yeah. And then we have to superimpose this case. Superimpose, what we do, equal and opposite of these will act on the structure, but this has to be hinge. This will be hinge again. So 3 by 8 WL, 5 by 8 WL in the opposite directions to what we find here. So we analyze this structure, structure number B, and the load vector for this has to be different now. Now you see along 1, 2, 3, 4, 5, 6, 7. So along the first degree of freedom, what is the first degree of freedom here? So is there any load here? No. Second degree of freedom, vertically up. Is there any load here? Yes, it is this 3 by 8 WL, but it's down. So that's why we have minus 3 by 8 WL. Third degree of freedom, any load? No, 0. Fourth degree of freedom, any load? No, it's also hinge. Fifth degree of freedom, any load? Where is the fifth degree of freedom? Is here. Horizontal. So no load.
Shouldn't it be
Let me
minus 5 by
complete.
8?
6 degree of freedom. 6 degree of freedom is vertical up. So 6 degree of freedom, load is 5 by 8 WL down. So it is minus 5 by 8 WL. And the 7th degree of freedom, we have WL square by 8 positive. So WL square by 8. So is this clear?
Yes, yes.
Alright. So now
Yes, yes.
now it's up to you which choice you want. You can, both choices you will get same answer in the end, either by this method, either by choosing your fixed ended case like this, or you choose your fixed ended case like this. The final answer will be same. Alright. Final answer will be same. Only thing is that here you will have to do superposition or correction for the displacement also. Okay, and this correction was not needed in the first case. So first case, I am just going again. So first case there was no displacement because we had locked here this. There was no rotation, no displacement because we had imposed a boundary condition here also. Okay, so that was the difference. So but both the choices, the answer will be same. So you stick to one choice, and if there is any confusion, you stick to the method which you can relate yourself well. Okay, now we do with method number 2, where we modify. So method 2 is that we modify KL. So we have modified KL and we mark it with star, that this is our modified KL. So how do we modify our KL? That if the member is like this, that it has one end hinge. This is our member, and we have the member like this, that this is hinge and this is not hinge, and we know that this is going to be always without any moment. So here we will derive the matrix in a different way, like we had derived in the class. So if you want, you can derive yourself and we can derive together again. So let's derive this matrix KL again. So it will be 6 by 6 but modified matrix. KL star 1, 2, 3, 4, 5, 6. and this side also 1 2 3 4 5 and 6. So I just label here 1 2 3 4 5 6 and 1 2 3 4 5 6. So the members will be different. Here will be EA by L, this is EA by L, and all others 0. Yeah, here minus EA by L. And what will be second? What will be the second term? Last time we had derived, so what we have to do, we have to give here force such that to derive the second column we apply delta 2 equal to 1 and others 0. So how do we take it? So it will be like this, that we fix all the degrees of freedom and give it cantilever kind of displacement, that this remains hinge. So this force required will be K22. So we had derived that time that this will be 3 EI by L cube. And what will be 3? 3 will be 0. What will be 4? 4 will also be 0. 5. 5 is basically this force, so it will be minus 3 I by L cube. And what will be 6? 6 will be positive, that is 3 EI by L square. So the matrix is now different. And similarly for the 3, third row and third column will be 0, all zeros, because always there won't be any force along the third degree of freedom when you give unit displacement to other degrees of freedom. So third row will be 0, third column will also be 0. I am just giving a pause. Gone. Now 4 will be EA by L and 0 0. 5 will be that we have to give displacement in the other way, that is keeping this as hinge, so we give displacement like this. So this will again be 3 EI by L square, sorry, 3 EI by L cube, and this will be 3 EI by L square. And what will be K66? K66 will be 3 EI by L from the slope deflection equations. So this is our modified stiffness matrix, and now we come to our structure. So this is our structure. With the loading as before, and now we mark the degrees of freedom. How do we mark the degrees of freedom? Now when we mark the degrees of freedom, we do like this. This is our degree of freedom number 1. This is our degree of freedom number 2. And where will be 3 now? My question is, where will be 3? Just you can guess.
Other joint.
No 3 here now. We have to skip the rotation here. We have to all together skip the rotation here, and 3 will be here now.
And there are other joint.
Yes, correct.
And there are
3,
other
4, 5. And then we have the reactions 6, 7, 8. And 9, 10, 11. So we have skipped the rotation here. Why? Because if we don't skip, we will be in a problem, because we will get runtime error. We have already discussed why, so we have to skip this. So we will not get any rotation here. So as compared to the previous approach in the end we were getting the rotation here, but now we will not be getting any rotation. So here correction will also become meaningless, like when we do the correction for the member and forces, member and displacement. So here there won't be any need for correction also. So we now split into 2 parts. One part is this structure I am just making smaller. This is our A and B. So this is A, where we have the hinge I just make in red color, and with the loading. So we have the loading here. This is A, and what is B? So B is this. Of course, we have to apply distance also. I will just do. This is B, equal and opposite of the reaction. So how we apply restraints? So we have to lock this. This joint we lock, but this we don't lock, because we have to retain hinge here, because we have skipped this degree of freedom. So if we lock this, then we'll have contradiction. So we keep it like this, hinge, and we get here the forces, fixed ended forces, WL by 3 by 8 WL, 5 by 8 WL, and WL square by 8. Opposite of these we are applying on the structure, 3 by 8, 5 by 8 WL, and here we have the moment, WL square by 8. Okay, so this is 5 by 8 WL and 3 by 8 WL. Okay, so this is our B. So we analyze B with the matrix approach using direct stiffness approach, DSA, and in the end we superimpose the results with case A. This is our case A. Alright, so when we analyze these, so now the procedure is the same. You have to form the force vector. So only thing is that when you are forming the force vector, the size is 1 less as compared to the previous case. So you can form yourself and it will be same. And then once we have done it, then solve the system equations. So after you solve the system of equations, you get UP and you get the reactions, and after you do this, then you get the member and forces. You get all the member and forces, and then the correction. When it comes to correction, we have to apply only the force correction. Fixed ended force correction needed. The displacement correction will not be needed, because here we are anyway not getting any displacement. Because we are not getting, there is no degree of freedom associated with the displacement here, so we don't get anything. So no question of any displacement correction. So in this method, in the end, we will not get any displacement. But now, before we go further, we have to be very sure which members we will use modified stiffness matrix. So we have member number 1, member number 2, member number 3. So which members should you use modified stiffness matrix, and for which members the normal stiffness matrix? Just tell me. Unmute yourself and tell me.
Member 2 will be modified.
Member 2 will be modified.
Yes, so 1 we have to use modified.
1 and 2, sir.
And 1 also we have to use modified. Okay, but then how do we use modified? See, modified, our assumption is that the hinges in the left joint, are the first joint at the near end, and the far end does not have hinge, so it fits well with member number 2. So member number 2, we assume that our local coordinate axis is like this. This is our local coordinate axis, that this is our x axis, local x axis, x dash, and this is our local y axis, y dash, and z axis is towards viewer. Now how about member number 1? Member number 1, what should be the local x axis? What should be local x axis? Tell me. Up or down?
Down.
Why down?
Down.
Up.
Why up?
Up.
See, our modified stiffness matrix we have derived with the assumption that near end is hinge, far end is not hinge. So that's why we have no choice, but we have to keep our axis such that our local x axis is down. Local axis is down. because then only
Yes,
we have hinge at the near end. Okay, and where will be now local y-axis? Local y-axis will be to the right or to the left?
Right.
Yes, it has to be towards the right.
Right.
Yes, y dash, because x cross
Right.
y will be z, will be towards you. Okay, so this is how we have to define the local coordinate system for members 1 and 2, because they are hinge, and that's why especially we have to define like this. 3 we have choice. 3 we can keep the other way also. 3 we can keep the local x-axis like this and local y-axis the other way, opposite to this. But for 1 and 2 we have to be very sure. Otherwise, if you want to keep, for member number 1, if you want to keep the local coordinate system up, local x-axis up, in that case you have to redefine the KL. KL will be different. KL you have to redefine for that condition that the far end is hinge. It will be different from what we have used here. Alright, so this is understood. So now I am just changing the camera, and now you can ask any questions. So luckily there was no technical glitch. You know, I have bought a new this camera, document camera. You are seeing this document camera. This is the new document camera. It is a very advanced version, very high tech. So now if you have any question, just let me know. You can ask any set of questions.
Sir, we have to apply the method.
Sir, we have to apply the method 2 only when there is
You have
hinge
choice.
frame.
You can apply method number 1. You can apply method number 2. Depends on which method you are strong in. In the exam, let's say I give you a question. I will not tell you that I will not force you to use any method. It's your choice. You can apply method number 1, method number 2. And within method number 1 also, you can have either both the ends restrained or only one end hinge, one end restrained. So I have given you all the possibilities, and it's up to you to choose what you want to use. Alright? Any other question? Dr. Dhawan? Dr. Dhawan, you hope you are around? I'm now coming in the main window, and I'm unsharing my document camera. Okay, Dr. Dhawan, are you hearing? You are mute. Dr. Dhawan, please come in the camera. I want to introduce you.
Yes, yes.
Please
Now-
come in the camera.
Okay.
I want to introduce you.
Okay. I'll just. Am I there?
No.
Am I there?
I think, please do again. I'll put you in the spotlight, and then you can address the students. So Dr. Dhawan is a very senior member of our department
Okay.
and institute. Everyone knows him very well. Yes. So I am just putting Dr. Dhawan in the spotlight. Yes, you were there in the camera, but again disappeared.
I'll again.
Yes, you are now there.
Yes. I think I'm
Yes,
there now.
I am now putting you in the spotlight.
So,
Yes,
friends.
you are now visible. So please say a few
Okay.
words to the students.
Yes, friend.
Yes, gentlemen, this is a very interesting.
Yes, gentlemen, this is a very interesting and useful course, advanced structure analysis, where he has tried to tell you so far how to work out the degree of freedom. And then today he has given you the example which he has solved in your presence, and how to generate matrix, and then how to work out the displacements. Here, see, unknowns are displacements, and that is the one which you need to work out. He has completely highlighted how you work out right from first step till end, and now you have to practice yourself. And in case you have any problem, you can discuss with me also.
Okay, so thank you, Dr.
Later.
Dhawan. Thank you. I'll just continue
Okay,
with
sir.
some words. Yeah, now I'm back. So Dr. Dhawan, he has been working with the stiffness approach for last 40-50 years. High-rise building with multiple degrees of freedom, and those were the days when the computers were not the way they are today. Those days all the input file had to be made in the form of the punching cards, right? It was called punching cards. Yeah, punching cards, and it was that's how they were entered. And there was only one or two computers in Delhi, IT being one of the place where computer was there. So that's how the things were done. So Dr. Dhawan is associated with this approach for last so many years. So once we finish this, so I have requested Dr. Dhawan to present a special lecture on analysis of ultra high rise buildings. High rise buildings does not mean 20, 30, 40 stories. He will tell you the latest in the analysis of high rise buildings like the Burj Khalifa Tower of Dubai. So that's what he has a lot of knowledge. So he especially consented to be part of our group. So thank you very much. So Monday again we'll have similar kind of lecture. We'll continue some more examples, and then Wednesday we'll have our usual talk. So when I was coming for today's class, 10 minutes before I had some technical glitch. So this is the risk involved in the synchronous mode, that if there is a technical glitch with the camera or something, then the lecture gets spoiled. But today nothing happened and there was no technical glitch, so we must thank God for that. Otherwise you have seen that on Monday I had some technical glitch, I was not able to log in, but then I had already pre-recorded lecture, so there was no there was a cushion. So let's meet again on Monday. Okay, so this is being recorded and I will just upload this on the or Impartis also. Thank you very much.